Welcome to this sixth lecture of the course Applied Stochastic Differential Equations. The topic of this lecture is Bayesian inference in SDE models, and we take the Bayesian filtering and smoothing point of view in this lecture. We start with an introduction to using SDEs as dynamic models in filtering and smoothing problems. We then proceed to discrete-time Bayesian filtering methods, and then to discrete-time Bayesian smoothing methods. Then we proceed to something called continuous discrete-time Bayesian filtering and smoothing methods, and then to continuous time Bayesian filtering and smoothing methods. Finally, we discuss related topics and summarize the lecture. We will now start with the introduction to SDEs as dynamic models in filtering and smoothing problems. The basic idea is to use an SDE as a prior model for a dynamic system. For example, if we have a car, like on the right, it has certain dynamics that we can basically write down if we know the laws of physics. However, the dynamics are uncertain, and we will model those uncertainties in the dynamics using a stochastic process. We measure the state of the SDE or the state of the car, for example, through some kind of measurement model. We might, for example, have a radar as shown on the right. We now aim to determine the conditional distribution of the trajectory of the dynamic phenomenon, for example, of the car, given the measurements. Because the trajectory is an infinite dimensional random variable, we don't want to form the full posterior distribution of the trajectory. Instead, we target to time marginals of the posterior distribution, and this is the idea of something called stochastic filtering theory, which is the topic of this lecture. In stochastic filtering theory or Bayesian filtering theory, we often characterize different filtering and smoothing problems in terms of if you have a continuous or discrete dynamics and continuous or discrete measurements. So in continuous time filtering and smoothing problems, the dynamics are modeled as continuous time stochastic processes, and the measurements are modeled as continuous time stochastic processes. Typically, these processes are SDEs. In continuous discrete time models, the dynamics are modeled as continuous time processes, typically SDEs, and the measurements are modeled as discrete time processes. In discrete time filtering and smoothing problems, the dynamics are modeled as discrete time processes, and the measurements are modeled as discrete time processes. However, these models are not completely mutually exclusive, because if we have continuous dynamics and discrete time measurements, for example, and if we are only interested in the values of the state on the measurement times, we can discretize the system just by solving the SDE at the measurement points, for example. Let's now take a look at an example of a state estimation problem on which we can formulate a filtering or smoothing problem as well. So we have a car like this with coordinates x1, x2, and what we know about the dynamics is that they obey the Newton's law. Force is equal to mass times the acceleration. But now the forces are unknown, and a natural way to model unknown processes is to replace them with stochastic processes. So let's model force divided by m as a two-dimensional white noise process. So if we substitute this into the Newton's law, we get that the second derivative of x1 is equal to white noise 1, and the second derivative of x2 is equal to the white noise 2. Now we can rewrite this equation as a first-order equation like this. So we define new variables x3 is equal to the time derivative of x1, and x4 is equal to the time derivative of x2, which then results in this kind of four-dimensional vector differential equation. And now we can call this matrix as F, and this matrix as L, and we can then write this equation down in shorter form. So the time derivative of the state x, which contains x's from 1 to 4, is equal to matrix F times x plus L times W, where W contains W1 and W2, which are the white noise components. More rigorously, this can be interpreted as a Ito SDE of this form. In state estimation problems, we also measure some part of the state in a way or another. For example, in the case of the car, we can think that we obtain measurements of the position which are corrupted with some kind of noise processes, which models the uncertainties in the measurements. So the first measurement y1 is equal to x1 plus a noise, and the second measurement y2 is equal to x2 plus noise. We again model these noises as white noise processes, because we have no reason to assume that the noises should be correlated in time. This measurement model can now be written like this. So the vector of y's, which contains y1 and y2, is equal to matrix H, like this, times the state plus a vector of noises. The purpose of the matrix H is to pick the components x1 and x2 from the 4-dimensional vector. More rigorously, we can interpret this measurement model as an SDE. It tells that the differential of some process is equal to h times x times dt plus d eta. And now formally y is equal to dz dt. So the resulting model now has this kind of form. So we have a dynamic model dx is equal to fx dt plus L times d beta, and a measurement model dz is equal to h times x times dt plus d eta. Now this is a special case of a continuous time model of this form. So more generally, we might have a dynamic model dx is equal to f of x and t dt plus L of x and t times d beta, and a measurement model dz is equal to h of x and t dt plus d eta. We could even generalize this more, but this is the most generic form that we will consider. Now the first equation here defines the dynamics of the system. For example, the dynamics of the car, in our case, derived from the Newton's laws. And the second relates the measurements to the state. So in our case, we had a radar measuring noisy versions of the position of the car. Now the problem at hand is that given that we have observed z or y, what can we say in statistical sense about the hidden process x of t? So can we somehow estimate the process x of t without observing it and only observing z? It turns out that the right question to ask is that what is the posterior distribution of x of t given the noisy measurements of y or equivalent to z on some interval from 0 to t. This probabilistic or Bayesian solution is surprisingly old, as it dates back to the work of Stratonovich around 1950s. The same Stratonovich whose name we have seen in the alternative formulation of SDEs. The aim is usually to compute the filtering posterior distributions, which are the distributions of x of t when we only observe y at times before time t. But sometimes we are also often interested in the smoothing distributions, which are distribution of x at t star, where t star is somewhere on the interval. So this filtering distribution corresponds to estimating the state of the car in our example, given all the observations obtained so far. Whereas the smoothing distributions are batch solutions. So if you have observed a sequence of measurements or interval of measurements at certain time interval, and we are interested in estimating the state at some time inside the time interval. Note that we could also attempt to compute or formulate the full posterior distribution, the distribution of the whole trajectory x of t star when t star goes from 0 to t, given all the observations on the same time interval. But this full posterior distribution is not usually feasible nor sensible. Of course, the probability density of this distribution doesn't exist, and it's not feasible to compute either in many practical cases. Quite often it's more natural to assume that we obtain measurements at discrete time instance instead of continuously in time. This is because usually we need to sample the sensor measurements at certain discrete time instance instead of getting a continuous signal out from them. So we can now form a model where y1 at step k is equal to x1 process evaluated at tk time plus, say, a Gaussian noise. And then y2 measurement at time step k is equal to x2 evaluated at tk plus another Gaussian noise. And we can assume that the joint covariance of the Gaussian noises is matrix R. The measurement can now be written as yk is equal to h times x evaluated at tk plus a Gaussian noise. And the h matrix is the same as before. And in probabilistic or Bayesian notation, this model is quite often written as, so the probability density of yk given x at tk is equal to probability density of Gaussian distribution for yk with mean h times x of tk and covariance matrix R. Our model now has this kind of form. So we have a dynamic model which is a linear SDE, dx is equal to fx dt plus L times d beta, and a measurement model yk is equal to h times x at tk plus r, which is a discrete time measurement model. This is a special case of more generic continuous discrete time models of this kind of form. So we have a generic nonlinear SDE, dx is equal to f of x and t dt plus L of x and t times d beta. And the measurements are modeled by the conditional distribution of yk given x at tk. Typically, in this kind of models, we are interested in the filtering and smoothing distributions as well, which are now given as x at tk given all the measurements from 1 to k, or the smoothing distributions, which are the distributions of x at t star given all the observations from 1 to t, where the t star is on the interval from time 0 to tt. In principle, again, the full posterior distribution could also be considered, but we will now concentrate on the above distributions only. It now turns out that this model is actually weakly equivalent to a discrete time model. Recall that the solution to an SDE dx is equal to fx dt plus L times d beta is given like this. So x of t is equal to the matrix exponential of f times x at t0 plus the integral from t0 to t of matrix exponential of f times t minus tau times L times d beta. Now, if we set t to be equal to tk and t0 to be equal to tk minus 1, we get that x at tk is equal to the matrix exponential of f times tk minus 1 times x at tk minus 1 plus the integral of matrix exponential of f times t minus tau times L times d beta, which can seem to have the following form. So the next x at tk is equal to a matrix A k minus 1 times the previous state x tk minus 1 plus a Gaussian noise, where the Gaussian noise is defined to be the value of the integral above. So A k minus 1 is equal to the matrix exponential of f times tk minus 1, which is a given deterministic matrix. And this qk minus 1 is a zero mean Gaussian random variable with the covariance given by qk minus 1 is equal to the integral of the matrix exponential f t minus tau times lq L transpose and the matrix exponential of f times t minus tau transposed. We already saw this expression when we derived the covariance of the solution to a generic LTI stochastic differential equation. This means that we can write the linear state space model equivalently in this kind of discrete time form. So x at tk is equal to a matrix times x at tk minus 1 plus a Gaussian noise, and the measurements are still given as yk is equal to h times x at tk plus a Gaussian noise. And this is now a special case of discrete time models of this form. So we have a generic Markovian model for x, which is given by the transistor density x at tk given x at tk minus 1. And the measurements are defined by a measurement model, which is the conditional distribution of measurements yk given x at tk. But now, because SDEs are Markovian, the transistor densities are well defined, and the transistor densities for SDE models are actually the Green's functions for Fokker-Planck-Kolmogorov equations. So we can always do this kind of discretization. And also in this kind of discrete time filtering and smoothing models, we are often interested in the corresponding filtering and smoothing distributions, which now are defined only at the discretization points, which can, for example, be the measurement points. And sometimes we can also do the full posterior distribution, which is much better defined in this discrete time case than in continuous time case, but neither in this case it makes sense computationally.